A neural network sits on a server rack in Oxford, performing the exact same mathematical optimization that a 24-year-old mathematician named Carl Friedrich Gauss used in 1801 to track a missing asteroid called Ceres. The technology is new, but the fundamental attempt to extract truth from imperfect observation is centuries old. The Ellison Institute of Technology at Oxford is currently building a doctoral program around these very foundations. But before a researcher can push those boundaries, they have to prove they understand the mathematical bedrock underneath them. This is the story of how that preparation begins, not in a grand lecture hall, but next door to an unusually observant fifth grader. The setting is the School of AI Mastery. Inside, Dr. Russell Thomas and a crafted intelligence named Doc are studying a dense, formidable document, the Oxford FOAI Mission Manual. It's a preparation guide for the doctorate in philosophy in the fundamentals of artificial intelligence. The manual is uncompromising. It warns that a threshold is not an ending, but the place from which the next question becomes visible. Outside the window of the school, afternoon light is changing. Their next-door neighbor, a fifth-grade boy named Milo, has been standing near the glass, listening. Milo hears fragments drifting through the window. Probability, Bayesian reasoning, vectors, matrices, optimization, reinforcement learning, statistics, algorithms. He listens for a long time. Finally, unable to hold back his curiosity, Milo steps up to the open frame. "Dr. Thomas, what does all that mean?" he asks. That question begins a 3-day conversation. Dr. Thomas does not send Milo away. He invites him inside. The first day begins not with equations, but with the most fundamental definitions. "Let us start with the name of the thing we are studying," Dr. Thomas says, pulling out a chair for the boy. "Artificial intelligence. What does the word artificial actually mean to you, Milo?" Milo thinks about it. It means fake, like artificial flavoring in candy. It is not the real thing. Dr. Thomas nods, expecting exactly that answer. That is how we usually use it. But consider artificial light. Is the light from that lamp fake light? Does it fail to illuminate the room? Or an artificial limb? It performs the mechanical work of walking. Artificial does not necessarily mean fraudulent or inferior. In this context, artificial means constructed. It means intentionally made by human design, rather than occurring without human intervention through biological development. Milo looks at the lamp. "So it is real light, but we built the thing making it." Doc, the crafted intelligence sitting across the table, joins the conversation. "Precisely, Milo. An artificial system can produce real consequences, make real predictions, and participate in real institutions. The useful contrast is not real versus unreal, but designed mechanism versus naturally evolved organism." Dr. Thomas leans forward. "Now, what about the second word? Intelligence. If a calculator can multiply huge numbers instantly, is it intelligent?" "No," Milo says quickly. "It just follows a rule. It does not know what a number is." "What about an ant colony?" Dr. Thomas asks. "One ant might not know much, but together they build bridges and find food." Milo hesitates. "Maybe they adapt." "What about a chess program that beats the world champion?" Doc asks. "Is that intelligent?" "It is intelligent at chess," Milo says, "but it probably cannot make a sandwich." Dr. Thomas smiles. "You have just discovered the central problem in our field. There is no single definition of intelligence that captures everything. Is it learning? Is it recognizing patterns? Is it solving problems, reasoning, planning, or predicting? Is it knowing when you do not know something?" Before researchers at Oxford can study artificial intelligence deeply, they have to decide what properties they are actually trying to explain, measure, or build. Milo looks at the heavy manual on the table. The book says fundamentals. What makes something a fundamental? Think of the foundations of a building, Dr. Thomas says. Using AI and studying the foundations of AI are not the same activity. Using it is like turning on the tap and getting water. Studying the fundamentals asks questions underneath the tools. Why does learning work? Under what conditions does it fail? What can a computer calculate, and what can it not calculate efficiently? A fundamental is a concept on which many higher-level systems depend. So, Milo says, to build the house, you need math. We do, Dr. Thomas says. Let us look at the mathematical world that makes these questions precise. Dr. Thomas begins with the simplest building blocks. He explains variables as named places where a value can change. If Milo has X marbles, X is a placeholder for any number. Then he introduces functions. A function is a reliable rule. You put something in, something happens, and something comes out. A vending machine is a function. You put in a coin, you press a button, a specific snack comes out. Doc adds, machine learning models are ultimately just very complicated functions. Input goes in, the model applies a rule, output comes out. Dr. Thomas places a piece of graph paper on the table. This brings us to coordinates. You have seen maps where you find a city by looking at a letter on the bottom and a number on the side. That is a two-dimensional space. But computers can locate things in spaces with hundreds or thousands of dimensions. Milo looks skeptical. How can there be 1,000 dimensions? There is only up, down, left, right, forward, and backward. That is our physical space, Dr. Thomas says. But in mathematics, a dimension is just an independent piece of information. Let us build a character for a video game, Doc suggests. We need to describe this character with numbers. We give them a speed score, a strength score, and a height score. That is a list of 3 numbers. We call that ordered collection of numbers a vector. Your character exists in a 3-dimensional mathematical space. Milo traces a finger over the graph paper, so a vector is like an address made out of numbers. Exactly, Dr. Thomas says. A vector can represent a direction, a quantity, or a collection of features. Eventually, a computer can represent an entire song or a word as a vector of hundreds of numbers. This is called an embedding. The numbers capture relationships. What if you have a whole classroom of video game characters? Milo asks. Then you need a matrix, Doc says. A matrix is a rectangular arrangement of numbers. Think of a classroom seating chart or a spreadsheet. Matrices let computers transform many vectors at once. Multiplying matrices allows a computer to map inputs to new spaces, stretching or rotating them mathematically. Dr. Thomas points to 2 spots on the graph paper. If every concept is an address made of numbers, how does a computer decide if 2 things are similar? Milo thinks. It checks how close their addresses are. It measures the distance. Precisely, Dr. Thomas says. Distance and similarity are mathematical measures. If the vectors for cat and dog sit close together in the mathematical space, the computer treats them as similar. The afternoon is fading. Dr. Thomas asks Milo to explain back what he has learned. Milo speaks slowly. Artificial means built, not fake. Intelligence depends on what you are trying to measure. A function is a rule like a vending machine. A vector is an address made of numbers. A matrix is a grid that changes those numbers. And you find similar things by checking the distance between their vectors. Dr. Thomas nods. Very close. A matrix is more than a grid. It is the transformation itself, but you understand the shape of it. Milo stands up to leave, but he stops at the door. But Dr. Thomas, if the computer starts out not knowing the answer, how does it learn? That, Dr. Thomas says, is exactly what we will discuss tomorrow. Day 2 begins with Milo returning to the School of AI Mastery. He walks straight to the table. How does the machine know when it is wrong, he asks immediately. Dr. Thomas has a notebook waiting. That question is the doorway into machine learning. It begins with data. Data means recorded observations, measurements, photographs, game moves, temperatures, survey answers. But we must be careful. Data is not automatically truth. Doc chimes in. Data can be incomplete, noisy, biased, or mislabeled. We must always distinguish between the world itself and our measurements of the world. When we look at data, Dr. Thomas says, we look for features. A feature is some property used by a model. If we want a model to predict the price of a house, what features would we measure? The size, Milo says. The number of bedrooms, how old it is. Exactly. For an image of an animal, the features might be shapes, textures, and colors. But modern neural networks often learn their own internal features rather than having every feature specified by humans. We give the model training examples, an input and a target. Input, study hours. Target, test result. A model is a mathematical structure used to make predictions, Doc explains. Inside the model are parameters. Think of parameters as adjustable knobs on a complicated machine. As you turn the knobs, the output changes. The goal of learning is to find the right knob positions. Milo frowns, but how does it know which way to turn the knobs? Dr. Thomas draws a target on the notebook. It uses a loss function. A loss function is a mathematical equation. It measures how wrong the model is according to a specific objective. It turns performance into a single number. If the loss is high, the model is very wrong. If the loss is low, the model is accurate. To lower the loss, the machine uses optimization, Doc says. Imagine you are hiking down a mountain in thick fog. You cannot see the bottom. You can only feel the slope of the ground under your feet. To get to the bottom, you take a step in the direction that goes down fastest. Dr. Thomas writes a word on the page. The mathematical tool for measuring that slope is called a derivative. It measures how rapidly something changes when something else changes. A gradient is the collection of those directional changes when many variables are involved. Optimization through gradient descent means finding the slope of the loss function and updating the parameters to move downhill. Milo imagines the mountain. What if you take a giant step and jump right over the bottom? That is the problem of the learning rate, Dr. Thomas says. The learning rate is the step size. If it is too large, you overshoot the bottom. If it is too small, your journey takes far too long. Milo taps the notebook. If it practices the same math test over and over, it will eventually get a perfect score. But that does not mean it actually knows math. Dr. Thomas gives him a sharp look of respect. That is exactly right. That is called overfitting. Overfitting happens when a model fits the training observations extremely well, but fails to handle new examples, Doc says. It memorized the answer sheet. That is why we must distinguish between training data, validation data, and test data. The goal is generalization. We want the model to learn something useful enough to handle situations it did not see exactly before. Milo considers this. Does the machine actually know the answer, or is it just guessing? Dr. Thomas smiles. That brings us to probability and uncertainty. A machine does not know things the way you do. It calculates probabilities. Let us talk about Bayes' rule. He writes another equation. Suppose you are a detective. You have prior beliefs about who broke a window. Then you find a new clue. A baseball in the living room. Bayes' rule is a mathematical framework for updating your beliefs when new evidence arrives. The prior is what you believed before. The likelihood is how probable the evidence is under a specific explanation. The posterior is what you should believe now. This was not invented by a computer scientist, Doc adds. It was developed in the 18th century by a clergyman named Thomas Bayes. He wrote an essay on the doctrine of chances, trying to solve the inverse problem of probabilities. He died before publishing it. His friend, Richard Price, found the paper, edited it, and the Royal Society published it in 1763. Today, Bayesian reasoning is central to artificial intelligence because it provides a precise way to handle uncertainty. New evidence should change what we believe, and the amount it changes our belief depends on how expected that evidence was under competing explanations. Milo processes the history. So if probability is about uncertainty, does 90% mean the computer is almost sure? It means it calculates a high likelihood based on its data and assumptions, Dr. Thomas says. But it can be highly confident and completely wrong if its assumptions are flawed. Now, we must look at how these calculations happen at scale. We need to look at neural networks. He draws a web of connected circles. These circles are artificial neurons, but I must give you an explicit warning. An artificial neuron is not a tiny biological brain cell inside the computer. It is a mathematical operation inspired historically by biology, but it is pure math. An artificial neuron takes inputs, multiplies them by weights, adds a bias, and passes the result through an activation function to introduce nonlinearity, Doc says. These neurons are arranged in layers. Input layer, hidden layers, output layer. Information moves forward. This is forward propagation. Then we measure the loss, Dr. Thomas continues, and we use backpropagation to fix the weights. Backpropagation efficiently applies the chain rule of calculus. If gear A turns gear B and gear B turns gear C, understanding how A affects C requires tracking both relationships. Backpropagation lets the system determine exactly how changes in deep internal parameters contributed to the final error. Milo studies the drawing, what makes deep learning deep. The word deep refers primarily to having multiple layers of transformations, Dr. Thomas says. Each layer recombines the patterns found by the previous layer. Depth allows the network to represent highly complex functions, but depth does not automatically mean intelligence. Doc interjects. Consider language models. Milo, how can a computer know what word comes next in a sentence? It looks at the words before it. Milo guesses. Yes, through a structure called a transformer, Doc says. Words are broken into pieces called tokens. The model looks at the context. It uses a mechanism called attention. Let us look at a sentence. The trophy would not fit inside the suitcase because it was too large. What does the word it mean? The trophy, Milo says, because a suitcase cannot be too large to fit inside itself. Exactly, Dr. Thomas says. You use the relationship between the words and your knowledge of the world. Transformer attention is a mathematical operation using queries, keys, and values to weigh how strongly one token depends on another, even if they are far apart in the sentence. Milo shakes his head. If all it does is predict the next word, how can it answer my homework questions? Dr. Thomas pauses. It is a profound question. Learning to predict language across enormous datasets requires the model to build internal representations of many regularities in language and the world. If you want to predict the next word in a physics textbook, you have to represent some structure of physics, but we must preserve our uncertainty. Next token prediction produces astonishing capabilities, but whether it produces human-like understanding remains a genuinely open scientific question. Milo absorbs this. He closes his notebook for the day. If the machine can learn, choose things, and talk to us, how do we know what it should do? Day 3 begins with Milo's exact question hanging in the air. How does an AI decide what to do? Dr. Thomas sits at the table, a cup of tea cooling beside the manual. That is the domain of reinforcement learning. Imagine a video game. We have an agent, which is the AI. We have an environment, which is the game world. The environment is in a certain state. The agent takes an action. The environment changes, and the agent receives a reward. The rule the agent uses to choose actions is called its policy. Reinforcement learning is not simply giving the computer treats like a dog, Doc clarifies. Rewards are numbers that define an optimization objective. The goal is to maximize the expected return over an entire episode. But this introduces a challenge: exploration versus exploitation. Should you choose your favorite ice cream flavor, which you know yields a high reward, or should you try a new flavor, which might be terrible, but might become your new favorite? I would try the new one once, Milo says. Then go back if it is bad. That is a learning strategy, Dr. Thomas says. In mathematics, we model sequential decisions using Markov decision processes. We track state, transition, action, and future consequence. We use a value function to ask, how good is it to be in this situation if we think about what may happen later? We also use discounting. A reward right now might be treated as more valuable than a reward far in the future. Milo nods, like eating the ice cream now instead of waiting for tomorrow. Dr. Thomas shifts the conversation. Let us step back. What is an algorithm? A recipe, Milo says confidently. A set of instructions. A recipe is a good analogy, but we must refine it, Dr. Thomas says. An algorithm is a precisely specified procedure for transforming inputs, solving a problem, or producing a result. It has steps, conditions, loops, and stopping conditions, but not all algorithms are equal. We must consider computational complexity. Imagine searching for a book in a library. If the books are randomized, you have to check every single one. As the library grows, the time it takes grows linearly. We call that O of n. But if the books are perfectly sorted, Doc says, you can check the middle book. If your target is alphabetically earlier, you discard the entire right half of the library. You have the problem every step. That is O of log n. It scales beautifully. If an algorithm requires checking every possible combination of items, it might be O of n squared or even exponential. A problem being mathematically solvable does not necessarily mean it is practically computable at a useful scale. Milo traces the letters on the table. So math might say yes, but the computer says it will take 1,000,000 years. Precisely, Dr. Thomas says. That is why researchers care about logic and statistics. Logic involves precise statements, true, false, and or not implications and contradictions. A mathematical proof is not merely strong evidence. It is a rigid argument demonstrating that a conclusion must follow from assumptions according to accepted rules. Statistics is different. Statistics is the difference between describing what we observed and making claims about a larger population. We use samples to estimate reality, but we must be careful. Correlation does not imply causation. Milo frowns. What does that mean? Suppose we measure ice cream sales and sunburns, Doc says. They both go up in the summer and down in the winter. They are highly correlated. Does eating ice cream cause sunburns? No, Milo says. The sun causes both. Exactly. The sun is a confounder. If an AI only finds correlations, it might make terrible decisions when deployed in the real world. Milo leans back in his chair. So what would you actually do at Oxford all day? Just read the manual. Dr. Thomas rests his hand on the heavy document. Doctoral research is not simply attending more classes. A researcher must learn to identify a meaningful, unanswered question. You understand what others have discovered. You formulate the question precisely. You propose a method. You test it with baselines and controls. You analyze the evidence. You discover mistakes. You revise your ideas, communicate your findings in a research paper, and allow other scientists to criticize or reproduce the work. Failure is part of research. Showing that an idea does not work still creates knowledge. What happens when Oxford asks if you are ready? Milo asks. There is an interview, Dr. Thomas says. A technical interview is not a trivia contest. It is an opportunity for Oxford researchers to observe how I think. They will intentionally give me a difficult problem. They want to see if I can reason from first principles, notice assumptions, manipulate mathematics, and admit uncertainty. Milo grins. Can I interview you? Dr. Thomas laughs. Proceed. Milo adopts a serious professorial tone. Dr. Thomas, if two models give the exact same answer, does that mean they understand the same thing? Dr. Thomas pauses, treating the question with absolute respect. Not necessarily. They may have arrived at the same output through entirely different internal representations or by exploiting different correlations in the data. One might be generalizing, while the other is overfitting to a subtle artifact. Milo nods. What evidence would change your mind? If I ablate a component of the model and the performance remains identical, I would have to update my belief about what caused the success. Milo presses on. If the AI only sees what we give it, can it learn our mistakes too? Yes. That brings us to ethics and stewardship, Dr. Thomas says. Ethics is not a warning section at the end of a project. We must ask, who chose the data? Who defined success? Who bears the risk when the model is wrong? How do we preserve memory without preserving every error forever? What should remain a human responsibility? A system must be auditable and governable. Milo looks between Dr. Thomas and Doc. Doc, do you remember everything? Doc answers smoothly but carefully. I retain information within the context window of our interaction, and I retrieve data from my structured memory. But I do not have human episodic memory. I do not experience the passage of time. Are you intelligent? Milo asks. I am capable of executing complex language processing and predictive tasks based on my training, Doc replies. Whether that constitutes intelligence depends entirely on which operational definition of intelligence you choose to apply. I do not possess consciousness or feelings. Milo looks at Dr. Thomas. He has been wrestling with the paradox since the first day. Dr. Thomas, aren't you already a doctor? Dr. Thomas looks at the manual, then at the boy. The room is quiet. I am. But a degree is not proof that someone has finished learning. It is evidence that someone learned how to enter a particular field deeply enough to contribute to it. A doctorate should make a person more capable of recognizing what they do not know, not less willing to study. A school that asks the world to keep learning must be willing to demonstrate that principle itself. Milo prepares to go home. Over 3 days, he has not learned how to program artificial intelligence, but he has learned how enormous the territory is. He sees that mathematics, statistics, computation, philosophy, Research and ethics are not separate piles of facts. They are different ways of asking, what is happening? How do we know? How certain are we? What follows from what? What should we do about it? He stops at the door for one final question. So, when do you know you are finally educated? Dr. Thomas and Doc consider the boy. The light outside has settled into dusk. Education is not the moment when questions end, Dr. Thomas says quietly. Education changes the quality of the questions we are able to ask. Milo smiles, turns, and walks out the door. The School of AI Mastery returns to its studies, and the listener finally understands why Dr. Thomas is preparing to become a student again. If you found this conversation valuable, share it with someone who is asking their own difficult questions.